Hello, this is question 4 of the 2009 MAT. As shown in the diagram below, C is the parabola with equation y equals x squared. P is the point 0,1, that's marked on the picture. Q is the point a squared, that's marked on the picture, and it moves around. L is normal to C, passing through Q. Okay, so there's nothing in that description that isn't on the picture. Find the equation of L. Okay, well, we've got a point on the line, so all we need is the gradient, and the gradient is perpendicular to the gradient of the parabola. Okay, so the equation then, what have we got? So for that'd be 2x. So the gradient, let's actually write it all out so I don't make a mistake. Gradient of C at Q is equal to 2x, which is 2a. So therefore we got the gradient of L at Q equals minus 1 over 2a. So if we just stick into y minus y1 equals mx minus x1 as our equation of a straight line, we can say that y minus a squared is equal to minus 1 over 2a x minus a. That's our equation of L. For what values of A does L pass through P? So we need this to be going through P. So that's going through 0, 1. Okay, so we would then have 1 minus a squared equal, this is for this bit, for the second part, is minus 1 over 2a, and then what was it, 0 minus a. Okay, so that is that. So what solutions? I mean, we know we're going to get 3 solutions as this is moving around. We're going to get one around about here, one around about here, and one there. So we've got 3 solutions. We always have to be careful when we've got an x is 0 solution on this, because yeah, it's kind of tempting, isn't it, to just cancel the, oh yeah, we can see, okay, right, this is because you've got this minus a divided by minus 2a here, so the temptation is just to say, yeah, this is a half. Well, it is, but the thing with that is you're then potentially doing a 0 divided by 0 when a is 0. So we know we've got a solution at a equals 0, so that's one of them. And then we can say, and now we can do the minus a divided by minus a and just get rid of them off of there. We can say, and 1 minus a squared is equal to a half. So a squared is equal to a half. So we got a is equal to plus or minus root 2 over 2. Yeah, which fits with the things I've marked on here on the picture. So that's quite good. So we've got 3 solutions. A is 0, and then a is plus or minus root 2 over 2, or 1 over root 2, whatever way you want to put it. Determine QP squared. So we want the distance, the square of the distance from Q to P as a function of A. Right, so that's going to be, well, we can just do this off of a triangle. So doing Pythagoras off of this, so Pythagoras, that is going to give us that QP squared is going to be equal to a squared, and then we're going to have our change in y, well, a squared because that's the x bit, the change in y is a squared minus 1, so we're going to want to do a squared minus 1 squared. So that's our QP squared. This is going along swimmingly. Find the values of a for which this is smallest. Right, let's get a clean sheet for this. So we've got a squared plus a squared minus 1 squared. That's what we're looking at here. So a squared plus a squared minus 1 squared. That's our QP squared. And we want to minimize this. So we're going to want to get QP on its own because we're just minimizing QP, not QP squared. And then we're going to want to differentiate. So we've got that QP is then going to be just the square root of this. I don't really fancy just differentiating that, so I'm going to expand out this bracket. So we're going to have a squared, explained out this bit, a to the 4 minus 2a squared plus 1. That's all going to be to the power of a half. Now we can do dqp dA, differentiate with respect to a. So we'll have a half times the differential of the, oh, actually that cancels with that. We've got a minus a squared. Differential of the contents of the bracket, 4a cubed minus 2a, multiplied by the bracket to the new power, minus a half. So we want this to be equal to 0. Okay, we have got an issue. I don't really fancy, I suppose we could differentiate that again. It wouldn't be out of the question. We'd do a bit of quotient on it or something, or a product rule. But I don't really fancy that unless we have to, because it is quite complicated. So let's just get stationary points then. So stationary when this is equal to 0. So, well, we've got a, this is a fraction. So it's only going to be stationary when the numerator, that bit, is equal to 0. So we've got a is 0, or we've got, if we cancel the a's, that will be saying that 4a squared is 2, a squared is a half. So a, oh, we're back to our plus or minus root 2 over 2. So they're our options for this. Are they all going to be minima or not? Because we could have, we know we've got these three, the same 3 points have come up again. This is where they're perpendicular. But it could be, we certainly, some of them have got to be, one or more of them has got to be minimal, because we know we've got global maxima if we go off to A being very large, positive or negative. They're our global maxima. So let's just look at these values and then something, so we can say one or more must be minimum. So let's look at the numbers. Let's stick these numbers here, these values of A, into there and see what QPs we get. So if A equals 0, well, we know that QP is going to be 1. That's just by looking at the picture. If A is root 2 over 2, then we're going to get that QP is equal to the square root of, well, we square that, we get a half plus a half minus 1 squared. So that is, well, let's write it out, a half minus 1 squared. That's going to be what our QP is. So that's minus a half squared gives us a quarter. So that's actually root 3 over 2. We're going to get, this is symmetrical, even if we have the negative root 2 over 2, because we're squaring the a's, we're going to get the same. So, and same for a equals minus root 2 over 2. So this is not a minimum, this one. That's not a minimum. That's going to be a local maximum then. So it's going to be, we're going to have a minimum here. We're going to have a minimum there. It's going to be increasing either way. If we're going this way, we're just, or up here, we're just increasing forever. Here we go to a local maximum at that point. So that's going to be what's happening at A is 0. And then we're coming back to the other minimum on the other side. So this is just plus or minus root 2 over 2 for that. Okay, didn't have to do the second derivative, which is what we're hoping to avoid. Last part, find a point R in the XY plane, but not on C. So somewhere in our Cartesian coordinates of X and Y, such that RQ, okay, is smallest for a unique value of A. Briefly justify your answer. Right, so Q's moving around, and we want RQ to be smallest for a unique value of A. RQ to be smallest for a unique value of A. Find a point R. So that's going to be anywhere which is below the curve on L. That would work, wouldn't it? Because you think about it here, so we're saying we want to have some point R. We take L where it is at the moment. We want to have some point R in the XY plane. That just means any point on the graph. So, but not on C, such that RQ is smallest for a unique value of A. Actually, you could, well, you can pick anywhere, can't you? I mean, it's RQ is smallest for a unique, as long as it's on L, but L's going to, does L cover every point? You just need anything on L. It doesn't even matter if it's above the curve, does it? I mean, if it's there. Ah, but it would do if you got in the middle. So you can't have anything on the positive y-axis because that would be even either side. But this bit has got one value. That bit has got one value where it's going to be closest to Q for a particular value of A. So providing we're on L, we're fine. So what's going to be, we need to actually find a point. I don't really want to do a calculation. So as this line moves around, it's going to come down here. Let's just say anything on the negative y-axis. So yeah, so any point on L as A changes, as long as, except when L is on positive y-axis. So we certainly can't have that. But we could have anything on the negative y-axis, any point on negative y-axis, e.g. 0, -1. That would work out fine because then that's going to be closest when A is 0. We might even want to put that in afterwards. So we can say closest to, what was it, C, when A equals 0. Right. That was a really weird way of wording that question. Something that was fairly obvious in that we can say 0 - 1 is only going to be closest to Q when Q is when A is 0. Yeah, that's just, I don't know, it's kind of weird, isn't it? The way they phrase that. But have I definitely read that right? RQ is smallest for a unique value of A. Yeah, so it is going to be smallest for a unique value of A. It's only going to have its minimum distance. I wonder if that works over here. RQ, again, it would do. It would do. We just didn't have to work it out. If we put R over here, we still could have worked out where R was, found some position on L, provided it was on the equation of our line. RQ would be smallest for a unique value of A. Yeah, that's fine. It just has to be perpendicular to the curve at some point. Right, okay, I'm happy with that. I think it was the way they phrased the question is a very odd way of putting it for something that's fairly obvious, especially if we just have to pick out a value, a point R. So I'll go for 0 - 1. Yeah, that was an okay sort of question. I think it was easier than the last one. There wasn't that much going on. Okay, it was a bit of calculus there that was maybe a bit more involved than some of the previous questions, but all in all, that one wasn't so bad, even taking into account the weird last part of the question.